Hello there! So far in this series of videos about logic, we've talked about conjunctions, that is, logical AND statements, where something and something else are both supposedly true, OR statements, that is, disjunctions, which say that something or something else is true, and negations or not statements. We've also seen how to translate such statements into symbols. And in this video, we're going to be evaluating these statements to see whether the whole thing comes out having the value of true or false. And we'll be doing this using truth tables. What are truth tables? Well, maybe you're familiar with things like multiplication tables. So when you learn your basic facts of multiplication, or addition, or subtraction, maybe you've seen them spelled out in tables like this, or maybe like this, so that you can look on the table and see, oh, 5 times 4 is 20, or 3 times 9 is 27. So you have all your basic multiplication facts there in convenient table form, where you can look up and see what the value of any number times any other number comes out to be. So a truth table would be kind of like this, where instead of giving values for where you multiply or add or subtract or whatever, they give values for when you AND or two simple statements together. So a table for AND values, that is conjunction values, might look like this, or it might look like this. And it's a lot smaller than those multiplication tables I was showing you, because with multiplication there was all sorts of different numbers we can multiply together. But with AND, there's only 2 possible values for each of the individual things that we're ANDing together. Each one could just be either true or false. So altogether, there's only 4 possibilities: true and true, true and false, false and true, false and false. That's it. So an expression like P and Q, to know whether that comes out to be true or false, you just need to know what happens when P and Q are both true, what happens when P is true and Q is false, what happens when P is false and Q is true, and what happens when they're both false. So this handy table here shows us that true and true equals true, true and false equals false, false and true equals false, and false and false equals false. Remember, with AND, both parts have to be true for the whole thing to be considered true. Otherwise, the whole thing is false. With OR, true or true equals true, true or false equals true, false or true equals true, false or false equals false. The disjunction is true whenever P is true or Q is true. And then for negation, not true equals false, and not false equals true. Now, do you remember in, say, basic algebra, being asked to evaluate an algebraic expression when the letters or variables in that expression stand for particular numbers? Like, for example, find the value of a plus b if a equals 5 and b equals 7. So you'd take your expression a plus b, you'd plug in 5 for A and 7 for B, so it looks like 5 plus 7, and then that equals 12. What about evaluating B squared minus 4AC when A is 1, B is 6, and C is 9? So you take your expression B squared minus 4AC, put in 1 in place of A, 6 in place of B, and 9 in place of C. So you're evaluating 6 squared minus 4 times 1 times 9. Well, 6 squared is 36. 4 times 1 is 4 times 9 is 36. And finally, 36 minus 36 is 0. So we're going to be doing something like that, only instead of an algebraic expression where the letters stand for numbers that have numerical values, and then we'll be adding and subtracting and multiplying those values. We're going to take an expression where the letters or the variables stand for simple logical statements that can have the value either true or false. And then we're going to be anding them or oring them or knotting them together. So, for example, if P and Q are both false, let's evaluate P and Q. Is that true or false? Well, we can see right here on this truth table that if P is false and Q is false, we're looking at false, and that is equal to false. If turtles can fly is a false statement, and elephants can dance is also a false statement, what about the statement turtles can fly and elephants can dance? Would that be true or false? Well, that's really what we were just talking about, only instead of symbols, we've got some words here. But the words stand for statements false and false. Turtles can fly has the value false. Elephants can dance has the value false. So turtles can fly and elephants can dance would be false and false, which equals false. How about this? If P and Q are both true, is P or not Q true or false? Let's evaluate the compound statement P or not Q when we stick in true for P and true for Q. So then it looks like true or not true. Well, not true, the negation of true, would be false. So this equals true or false. And what is the value of true or false? Well, it's equal to true. So that's the answer. If P and Q are both true, P or not Q is equal to, it has the value true. If Paul is here is false, and Mary is here is true, is Paul is here or Mary is not here true or false? Well, let's translate this into symbols so we can work with it symbolically. This is something or not something, like P or not Q. Here I'm using P to stand for Paul is here. I'm using Q to stand for Mary is here, so that the negation of Q would be Mary is not here. And so this whole thing translates into P or not Q. P, that is Paul is here, has the value false. Mary is here has the value true. So this would be false or not true. Well, not true would be false, and then false or false equals false. So that's the value of the whole thing. Paul is here or Mary is not here is false. If P is true and Q and R are both false, what about R or P and not Q? Well, just like in algebra, we would evaluate what's inside the parentheses first. But first, let's stick in the actual values for P, Q, and R. Remember, P is true, Q and R are both false, so it looks like false or, and then in parentheses, true and not false. So inside the parentheses, first of all, not false would be true. True and true would be true. And finally, false or true would be true. So the whole thing evaluates to true. What is the value of P and not P or Q when both P and Q are true? What about when P is true and Q is false? What about when P is false and Q is true? What about when they're both false? Well, we could do each one of these individually, the way we did that last example, but since we want to know it for all four possibilities, let's just do this all at once systematically using a truth table. So really what we want is the value of this expression, P and not P or Q, in all four possible truth values of the P and the Q that make it up. So we're going to set up a truth table, and the first two columns are just showing us what the P and the Q individually are. So that's going to look like this. Then we're going to say what the negation of P is, and we're going to then work out the negation of P or Q, the expression inside the parentheses. And finally, we're going to put that together with P and that expression. And that'll be the value of the whole thing. So to start with, we're going to fill in true, 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 false, false, true, false, false. Those are the four possible truth values for P and Q individually. Now look at the value of P and negate that, that is, take its opposite to fill in the value for not P. In the first row, P is true, so not P would be false. In the second row of the table, P is still true, so the negation is still false. In the third row, P is false, so the negation is true. Fourth row, not false is true. Now for the value of not P or Q, here we have the value for not P, and in this column we have the value for Q, and we just have to OR those values together. So look at what's here, look at what's here, and take their disjunction. False or true equals true. False or false equals false. True or true equals true. True or false equals true. Now we need P and that thing. So look at the column that tells us what P is. Look at the column that tells us the value of not P or Q, and those together. So true and true equals true. True and false equals false. False and true equals false. False and true equals false. So in this last column, we have the value of the whole thing, the whole expression P and not P or Q for each possible individual value of P and Q. And I noticed that those values, true, false, 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 exactly match the truth values of just P and Q. So this somewhat complicated looking expression is logically equivalent to just P and Q. It's true whenever P and Q is true, and it's false whenever P and Q is false. Let's try another example. Let's make a truth table for P or Q and not Q. So we're going to look at P and Q individually. We're going to evaluate P or Q. We're going to evaluate not Q, and then we're going to AND those together. So here are the possibilities for P and Q individually. Now for P or Q, true or true is true, true or false is true, false or true is true, false or false is false. Now we need not Q, and that's the opposite of whatever Q is. Not true is false, not false is true, not true is false, not false is true. Now look at those two columns, the column for P or Q and the column for not Q, and AND those together. True and false is false. True and true is true. True and false is false. False and true is false. So that last column gives us the value of the whole expression, the whole compound statement in each case. Now here we've been doing this ourselves, but there are applications that can make truth tables for you. One such is the Wolfram Alpha application or website. I can go to wolframalpha.com and type in P or Q and not Q, and it will make me a truth table.